just a small town girl living in a lonely world. She took the midnight train going anywhere. Just a city boy, born and raised in South Detroit. He took the midnight train going anywhere. A singer in a smoky room, a smell of wine and cheap perfume. For a smile they can share the night. It goes on and on and on and on. Strangers waiting up and down the boulevard. Their shadows searching in the night. Streetlights, people living just to find emotion, hiding somewhere in the night. Working hard to get my fill. Everybody wants a thrill. Paying anything to roll the dice. Just one more time. Some will win, some will lose. Some are born to sing the blues. Oh, the movie never ends. It goes on and on and on and on. Strangers waiting up and down the boulevard. Their shadows
Okay, let's get started with lecture. Perfect. Okay, so quick reminders. Homework, self-grades are due tonight at midnight. We've been getting a lot of requests for regrades, and I wanted to remind everyone that, we're offering this regrade to be nice to you, but if every single person in the class asks for a regrade, this will quickly become unsustainable, and we might stop offering this option at all. So please be conscientious when you ask for your homework to be regraded. There are actual people doing the actual grading, and we're trying really, really hard to make sure that we actually give you the right grades. And please remember to follow the instructions. I know that it can be a pain to use Gradescope, but this is what we have to do to be able to actually handle a class of this size. If we were to manually sit and grade homeworks, then we would almost certainly lose one piece of paper somewhere for someone. And that would really, really be unfair. And doing it electronically in a way that requires you to submit, one page at a time is the only way we can guarantee being fair to you. It's not like this is something that is super easy on our end either. We're just doing it to try and make sure that we can actually grade every person's homework. So please try and be considerate about this. And, I know that there is a process of submitting the homework which can be painful. It's not that we don't recognize this, but it's the best option we have. And hopefully if you just start submitting your homework a little bit earlier, like at 11 p.m. instead of right at midnight, this will be better for everyone. Second, there's a Piazza post on the change in the lab schedule. So everyone, please read this post and make sure you go to the right labs at the right time. The lab you're going to do this coming week is going to be one of the coolest labs, personally, I think. Just the way it's been designed and how it connects up all the different parts of the class, I think is really exciting. And we're going to start talking today about eigenvalues, which is really going to be kind of the crux of the lab that you're going to do in the upcoming week. Finally, there's been questions about extra credit. We definitely encourage extra credit submissions. There'll be a lot of material, for example, in the lecture covered today that could, lead to extra credit demos. We have updated the Piazza post about extra credit for content creation as well. So if you have further questions about that, please go and read the Piazza post. Okay, so hopefully all of you saw in discussion a lot more about null spaces and have started to get a feel for what a vector space is, what a null space is, what a basis is. And these terms, or this, what seems like jargon, is something that is actually going to end up being very useful, and that is what this lecture is going to start covering. I got a lot of questions after a lecture, and I know a lot of the TAs got these questions as well, asking, well, why do we need to know what a null space is? What is the use of a null space? Where does it come up? And one answer to that is, well, of course, it is very, very useful in characterizing when you have a large family of equations. It helps you come up with a parametric solution when you have an infinitely many number of solutions for a given system of linear equations. What we're going to talk about today, you're going to see that null spaces will come up yet again, and you'll see exactly how and where they're particularly useful. So, yesterday when I was preparing for the lecture, I did a quick Google search, and what I looked for was, I looked to see how much is Google worth today. So, I'm curious, any guesses? I didn't know the answer. Every year when I teach this class, the number changes, so I have to look it up every time. 800 billion. Other guesses? People with laptops, you can't search. Well, the answer I found was actually 279.3 billion, but that's still a lot of billions. And Google, as of now, is running about 3.5 billion searches every day, up to 1.2 trillion searches every year. I had to write the numbers down so that I wouldn't forget them. But the question is, how many of you actually knew that this company, Google, was actually founded based on a key idea in linear algebra? It built off of a simple research paper that came out of Stanford that was thinking about, well, how do we try and understand traffic on the internet? How do we try and understand how people are, looking for information on the internet? How do we understand which web pages are more important than other web pages? And what we're going to talk about in class today, it's one of my favorite lectures in this entire class because it's finally all of this weeks of hard work coming together to understand something that, to me, is really, really impactful and really, really powerful. So what we're going to talk about today is we're going to try and actually understand the essence of what is called the PageRank algorithm. And this is the algorithm that Google uses to actually index its web pages on the internet and give to you, what is the most important or the most relevant web page. Of course, since this very first algorithm and the very first iteration of this, there have been many, many tweaks, and the algorithm has evolved significantly, and there's no way that we can cover all of that in this one class in a couple of lectures. But what we're going to try and do is going to try and give you the very essence of what really happens in the PageRank algorithm. So, what was really Google's challenge when they were trying to understand and index the web, right? How do they know which web pages are actually important and get a lot of traffic? And how do they understand which web pages are not so important and, should not be given as much importance? What they wanted to understand was, what are the web pages that people end up on after a lot of surfing? And what are the web pages that don't seem to get as much traffic? And what we've been building up to in the past few lectures is exactly to be able to try and solve this problem. So let's think of a very, very simple example. Let's think of the following example of two web pages. Let's say there's a web page A and a web page B, and let's say these web pages have in-links and out-links, right? So they have a certain number of links that can go from one page to another. So, let's say there is a link on page A that goes to page B. And let's say, sometimes web pages also link back to themselves, or they have, pages within themselves, certain domains have pages within themselves. So there's another link on page A that goes back to page A. And let's say page B links back to itself as well. So now if there's two links on web page A, let's say that, if there's two links, people will choose kind of one of the two links. So let's say half the traffic, that is half of the people that are currently on A, will end up on page B. And half of the people that are currently on A will again come back to being on page A. And for B, let's say that there's only one link. So if I go to B, I just click the link on B, and I come back to the link on page B. So we can say, maybe this is, this is the Stanford website, this is the Berkeley website, B for Berkeley. So you've seen these kind of pictures before. We're talking now about people surfing the web, but this is very much exactly the model that we used for understanding the water pumps example, right? It's exactly the same system. So we've written out these transition matrices many, many times. Can you quickly write out what the transition matrix for this is? Make sure you check your answer with your neighbor and make sure you wrote the same matrix out. How many people have the transition matrix down? Everyone? So someone want to call it out for me? Great, right? Half of the traffic from A goes back to A. That gives this one half. Half the traffic goes to B. 0 from B goes to A. And 1 from B goes to B. Great. So we know that x of t plus 1 is equal to q times x at time t. So let's say we have the following situation, right? Let's say that at time 1, all of the people are on the Stanford website. So how do we know how many people there are? We don't really know how many people there are, but we don't want to care about this too much. So we're just going to represent this as fractions. So we're going to say that x at time 0, let's say, is 1, 0. What this means is that fraction 1 of the total population is at the Stanford website, and fraction 0 of the total population is at the Berkeley website, right? And, so if there were a total of 100 people in the universe, there would be 100 people on A and 0 on B. If there were a total of 5 people, there would be 5 people on A and 0 people on B. Everyone with me there? Okay, so what will happen when the clock ticks? What will be the fractions of people on website A versus website B? I heard 1/2, 1/2. And how do we calculate this? We take Q times 1, 0, right? This is something we've done a lot, right? We're very used to, at this point, using a matrix as a transformation, right? What is this doing? The time ticks, the matrix acts as a transformation. Okay, what about x at time 2? What is x at time 2? 1/4, 3/4, right? What about x at time 3? What is happening to the fraction of people at website A at every time? 1/8, 7/8, right? X at time 3. So if you kept running this, where would you end up? So can you write this as a function of t? Can you write a general formula for x of t? Just observing the pattern here. Make sure you got the same answer as your neighbor. Talk for a minute. What do people have? Are people done? Okay, what do people have? 1/2 to the t, and then 1 minus 1/2 to the t. Right? Does everyone see how we got this? Every single time this top entry gets multiplied by 1/2, right? And the remaining fraction ends up in B. So if we have time keep going on, let's say t now goes to infinity. What are you going to have as x of infinity? Zero, 1, right? So where is everyone? At the Berkeley website. So, does it matter? So even though everyone started out at Stanford, where did everyone converge to eventually after they had done all their bouncing around? This is why you should come to class. The webcast could not hear that. Yes, question.
Won't there always be some stragglers on the other side, though, considering that we're working with the limit at infinity? Infinite division by 2 will still not quite leave us with no one on the Stanford
So if you had a very, very large number of people, the question is, will there be some stragglers on the first website? And if you had a very, very large number of people, you will always keep dividing it by 2. In this case, because at some point you won't be able to cut people in half. You're not going to actually end up with that. But your question is right. Like in the case of the water pumps, right? You will converge at a particular rate. So how fast you get to this steady state, as we're going to call it, is something that you will learn more about when you take classes like 126, as well as maybe like 229. All of these classes 226 will cover it. So these classes will talk more in detail about exactly how this convergence happens. We're not going to go into too much details talking about rates of convergence in this class, but the basic idea is that if you keep running it for long enough, you will eventually get to this state, 0, 1. Furthermore, once you get to the state 0, 1, can you change your state? Let's say I started out x of 0. So new case, right? New setting. X of 0. If everyone had already started off at the Berkeley website, what would happen at time 1? If at x of 0 you were at 0, 1. Right? You would still have x of 1 equal to 0, 1. X of 2 would also be 0, 1. X of 3 would also be 0, 1. So this state is somehow a special thing. It's a special state. And we call it a steady state. Sorry, remind me if I accidentally, you can't see on the up there. So we call this a steady state because basically it has the property of being steady. Once you enter that state, no matter how much time passes, you don't change. You don't go to any other state, right? And if you want to think about this in terms of matrix vector transformations, what does that mean? When this matrix Q multiplies this vector, what do you get out? You get out the same vector. So it's as though a transformation never happened. Is this true for all vectors? If I multiplied Q by any vector, would I get out the same vector? No. So there's something special about this, right? And this is exactly what we want to try and understand in the course of this class. So we see in this very simple example that clearly website B was the most popular. So which would be the highly indexed? What would be the top page that Google would want to surface when trying to return the results of a search query? Right? If no one is ever going to this page, if no one is ending up on that page, that must be less important than the Berkeley page. That's basically the idea behind the algorithm. So now, this is a very, very small, simple example. Yes? Question, okay. Is it still steady state if it's like a cycle of states? We will get to that question. Just pause on it for a little bit. Okay, so we have this simple case, but when we think about the internet, I know it would be very nice to have an internet with 2 web pages, but it would also not be very useful. So if you think about the internet, you usually have again, a very large number of web pages, right? And they're all connecting to each other. You have some interconnections. This is a very large interconnected web, which has much more than 9 websites, but 9 looked bigger than 2, and it was easier to draw. So when I have this large set of websites, how do I figure out, which website is more popular or less popular than the others. In this very simple case, right, even by just inspecting the graph, without doing any linear algebra, you were able to see which website was the more popular website, even ignoring your site information. But here, in this particular case, it's much more complex, right? How do we figure out if there's a steady state, if there's a particular distribution by which people are going to converge to different websites? So here, we're going to think about this, and this is exactly the problem that was posed, and we're going to think about this again in the same way that we've been thinking about it. So x at time t plus 1 here is some large matrix Q times x at time t. And this is going to be called the transformation matrix. And this is going to represent the fractions of people at time t in each of the... So the first entry of this represents the fraction of people on the first website, second website, so on and so forth. And this is the fractions of people at time t plus 1. And I keep coming back to this because I really want to emphasize this idea of matrix vector multiplication as not just some operation that you keep doing as algebra, but it really is this transformation of a space. This is why we define the notion of vector spaces. Because what we're doing is we're taking basically the vectors at time t, multiplying them by this matrix, and transforming them to a different, to this other vector space. It's a transformation. It's a mapping from one space into another. And this is what makes linear algebra so powerful, is because you can use it to model dynamical systems. So this is an example of a dynamical system where there's some dynamics. And you've seen this on the homework, right? You've seen this on the homework with, for example, the self-driving car problem, as well as I believe on the current homework there's some problems that talk exactly about this. There's the segue problem. So you're seeing basically that matrices can be used to transform states. So what we want to talk about now is when we start thinking about steady state, this is a special case of this transformation, right? It is a case where this transformation doesn't actually transform. So we want q times x of t, which is the next state, so x of t plus 1, and we want this to be in steady state. So we want it to be so that this is exactly equal to x of t, right? When we say steady state, what do we mean? Its state doesn't change. So we're saying that even after you apply the operator q, x doesn't change. Is this clear to everyone? I'm seeing some confused looks. Questions? Okay. Yeah, if you're confused about something, probably someone else is also confused about something. So, don't hesitate to ask questions. Yeah.
So basically, steady state, right? It's going to be more complex to figure out where it is, and it's going to be a lot harder to figure out which site is more popular with 9.
So what we're going to do now is exactly try and come up with an algorithm by which we can find out what the steady state distribution of people on these websites is. So it's hard, and we're exactly going to try and come up with an algorithm to be able to do this. So if we want to have this guy be true, right? If we want this, then can we rewrite this in some way that makes it look familiar to us? So what if I say, I write this as q times x of t minus x of t equal to 0. That was a big O. So, what does this look like? What have we seen that you are reminded of when you see this? Null spaces, right? So, what can we write this as? So, can I make this look like a matrix times a vector? So, this guy is x of t. If I wanted to make this look like a matrix times a vector, what would I write it as? I. So this is q times x of t minus I times x of t equal to 0. And because I have, associativity of matrix vector multiplication, the distributive law in particular, I can write q minus I times x of t equal to 0. And so now, what am I interested in finding to be able to find x of t such that x of t is in steady state? Null space, right? I want to find the null space of q minus I. So what was q again? We had q here as so you are all now null space experts. Why don't you go ahead and write down what q minus I is and tell me what the null space of q minus I is. Feel free to talk to your neighbors. How many people are done? How many people didn't do anything? Why? Okay, well, you have 30 seconds. You better be fast. No, I want you to do it. So what is this matrix Q minus I? Q minus I is negative 1/2, 0, 1/2, 0. Right? Did everyone get this as Q minus I? So, how do you find the null space of Q minus I? 1/2, 0, 0, x1, x2 equal to 0, 0. Gaussian elimination gives me negative 1/2, 0, 0, 0, 0, 0. So, what do I get? So I get x1, x2 is equal to What'd you get? 1, 0? 0, 1. What about, did anyone get like x equal to like 0, 313? Did anyone get that? You got it? Really? Okay, I didn't get this either, but does it work? Why does it work? What is the whole space of solutions that works? The span of 0, 1, right? So anything that is like this. So the span of 0, 1. So here, what is important about this 0, 1? Is it the exact vector or is it the direction of the vector? The direction, right? So what we care about when we're thinking about the null space of Q minus I is basically the subspace spanned by 0, 1. And this is a line, right? In R2, this subspace is going to show up as a line. Yeah, question?
Sorry, could you just clear up how you went from that matrix to the x1, x2, 0?
How did I go from...
From the Gaussian elimination to the answer.
How did I go from here to here? Oh, I just observed that basically there's one free parameter because there's one row of zeros. And so I can set basically, so I can set x2 equal to anything. We can call it, let's say, t. And so then I have minus 1/2 x1 so then if I have this, then I have x2 is this, so then I have 0 x minus 1/2 x1 plus 0 times x2 is equal to 0. x2 is fixed now as t. So x1, what must x1 be? 0, right? Because this, no matter what x2 is, this is going to be a 0. So that's why I have to have x1 be fixed at 0, but x2 can be any parameter, which is basically this any multiple of this vector. Does that make sense to everyone? Yeah. Okay. Good question. So now what we see in this null space, right? So now when we take, remember, we're not looking at the null space of Q. This is really, really important. We are not looking at the null space of Q. But when we get into this space, which is the space spanned by 0, 1. So let's give this some name. Let's just call this null space of Q minus I. So if we enter the null space of Q minus I, can you ever leave? If x of t belongs to this null space, can you ever leave? No, right? Q times alpha times 0, 1 always is going to give you a multiple of this same vector. Right? You're kind of always stuck in that space. And this is what we're going to define as an Eigen Space. And we're going to get to that a little bit in more detail. But here, what we're seeing is that basically this null space of Q minus I is called an Eigen Space of Q. Okay, so that was a really, really simple example. I want to now go to a second example, one that we've done in class many times before. So let's say now we have 3 websites, A, B, and C. I didn't figure out what these websites were, so maybe you can come up with an example. But let's say they have the following structure, where we have half of A going to B, half of A going to C, all of C goes to B, and all of B goes to A. So this is this thing we've seen before. What is the transition matrix for this? Zero, 1/2, 1, 0, 0, 0, 1, 0. And if I wanted to write x of t in terms of x of 0, let's say I start out in some initial state, and I want to write out x of t in terms of x of 0. What do I write this out as? Q times xt minus 1, but I want to have an x of 0 here. How many times do I have to apply the transformation q to x of 0 to get x of t? T times, right? So I apply it once, I get x1. I apply it twice, I get x2. So q times q times q times q times q. T times will give me x of t, right? So let's try and explore that a little bit. So can people see this? So what do I have here? What is this matrix that I'm writing out? It's the same matrix Q that we were talking about, right? And then what is this line doing? It's multiplying Q squared. What is this doing? And then what is this? Q to the 16. So if we try to go through this, so we get basically, this is Q. Then Q times Q, I get 0.5, 0.5, so it's different from Q. 0, 0.5, 0.5, 1, 0, 0. So this is what happens after after things run once. Then I get Q3 is here. Then I get Q4 is this. Q16, people can see this, right? It's big enough to see, right? Can I make this bigger? Okay, is this bigger? Yeah. People at the back? So what do you observe what's happening with these guys? There's a pattern developing. What is the pattern that's developing? There's some kind of steady state happening, right? What is going to happen if I keep raising Q to a power? I'm going to keep, as I keep doing this, I will keep. So now what happens if I do Q128 times Q128? Oh, sorry. So I'm going to keep getting the same thing, right? I keep raising it to higher and higher powers, but I keep getting back exactly the same matrix. So limit, if I write Q to the t as t goes to infinity, what is this? I get this 0.4, 0.4, 0.4, 0.4, 0.4, 0.4, 0.2, 0.2, 0.2. Right? So, is it a special thing that these columns are equal? Is there something special about this matrix Q, right? That's natural question to ask. Like, you don't expect to get equal columns. To me, that's surprising. You should be thinking, wait, what? Did she rig this example for 3 lectures in a row to set this up? So what happens if I do Q times 0.4, 0.4, 0.2? What do I get out? Can someone shout out the answers? What do I get out? Right? Steady state. Each column vector here is telling me what the steady state distribution of people on this set of websites is. And again, why are all of these columns the same? For this, we have to go back to trying to understand, again, matrices as transformations and the notion of basis. So when I think about this Q, right? When I think about this Q, what does the first column of Q represent? The first column of Q represents a particular transformation, right? It represents the transformation, what happens to this vector E1, 1, 0, 0. Right? If I take Q times 1, 0, 0, remember, matrix vector products say that 1, 0, 0 pulls out the first column of Q, right? Because I'm putting 0 weight on the second column, 0 weight on the third column. So Q times E1 gives me the first column. Let's call this column Q1. So the first column represents the transformation on 1, 0, 0. The second column represents the transformation on 0, 1, 0. And the third column represents the transformation on 0, 0, 1. So this is the case where we start with first all the people at A, or all the water at A. Second, E2 is when all the people are at B, or all the water is at B. C is when all the people, or E3 is when all the people are at C. Just so you know, you might see this word somewhere, these vectors are called elementary vectors. And what can you say about E1, E2, E3? They form a basis for R3, right? These form a basis for R3. And we saw, we talked about this before, but you can write any vector A, B, C in the coordinates of this basis, right? What are the coordinates of this basis? This is A times E1 plus B times E2 plus C times E3. So now, if I look at, with this in mind, if I look at Q to the T, right? What is that telling me? If I look at this matrix here, my steady state matrix, what does this column being 0.4, 0.4, 0.2 mean after you have remembered this interpretation of what a matrix represents? So the first column of Q to the T is where E1 gets mapped, right? So if I start out with all of the water in E1, where am I going to end up at? I'm going to end up with 0.4, 0.4, 0.2 across the 3 reservoirs, or across the 3 web pages. What happens when I start off with all of the people at the second web page? So these map to each other What about this one? This maps to this, and this maps to this. So what does that mean? The third column represents what would happen if your initial state, what would the state be at time t if your initial state was 0, 0, 1? So the fact that all of the columns are equal is saying that no matter how you start out, if you start out with all of your water at 1, or all of your water at A, or all of your water at B, or all of your water at C, if you run these pumps for long enough, or if you have all the people at A, all the people at B, all the people at C, if they keep surfing for a long time, they're all going to end up with, 0.4 of the people on website A, 0.4 of the people on website B, and 0.2 of the people on website C. It doesn't matter. The columns being equal say that no matter what your initial state was, you're going to end up in the same configuration. So it's not a coincidence that the columns are equal. It's a function of this steady state. Is that clear to everyone? So the question is, really, how can we find these steady states, right? That's really the main question that we want to try and understand. And for this, we want to try and understand this notion of eigenvalue. So what is an eigenvalue? So if I have a matrix A, and it operates on a vector V, and I get out something which is lambda times the vector V. So what does this say? This is a matrix vector transformation. And the vector I'm getting out is the scaled version of the same vector. So what we were looking at here was a special case. Here we were looking at a special case where the eigenvalue was 1. When I take q times x of t, I get 1 times x of t. But I want to think about this more generally. When A times some vector V equals to some lambda, maybe there is some scaling. I want to try and understand what this does, and how can we understand this notion. And this thing, this guy here, is called an eigenvalue. And now we can write this as A times V minus lambda times V equal to 0. And now we have A minus lambda times I times V equal to 0. And so the null space of A minus lambda I is the eigenspace associated with eigenvalue lambda. Yeah, question? Oh. So basically, if I was to draw this out for our previous example, right? If I have some three-dimensional space, and I have this vector, this is 0.4, 0.4, comma 0.2. When I multiply by A, what I get out also remains exactly on this line, right? This I have as the axis E1, E2, E3. So this line is a subspace in this three-dimensional space, and this corresponds to the null space of Q minus I for this matrix Q. So the question is now, can we really understand what all of the steady states are? We've done some calculations. We found one steady state. But can we really characterize this completely? And it turns out that basically all solutions to this will help us try and understand all of the steady states. So let me try and write this matrix out. A minus lambda I. Let's call this matrix B. Okay? And when I think about B times V, I can write it out in the following way, right? I can think about the column vector B1, B2, Bn times this vector V. This is equal to 0. And now we want to try and understand, when is this possible? But now there's two things in this setup that we don't know, right? What are we given? In this case, what we're given is A, right? We're given some matrix A. We were told what A is. But what do we not know? There's three things here. There's A, there's V, and there's lambda. A is something we know. What are the things that we don't know here? We do not know lambda. We do not know this guy. But do we know V? We don't really know V either, right? We want to solve this equation. There's an unknown here, lambda, and then there's this entire V vector that we don't know. So we had to come up with a new algorithm to be able to actually solve this. Our standard strategy, like so far what we've been doing, when we see some unknowns, what do we try and do? We try and do Gaussian elimination, right? But this isn't quite exactly fitting into the framework of Gaussian elimination. So we have to try and be a little bit more creative and understand more what these transformations are doing to be able to actually solve this. So if I want to find some lambda, find a lambda such that this is true, right? B times V is equal to 0. This won't be true for every lambda. It'll only be true for some lambdas. But if I have a set of column vectors B, and I know that B times V is equal to 0, what can I say about the column vectors of B? They must be linearly dependent, right? If B1, B2, Bn times V, for some non-zero V is equal to 0, that means that B1, B2, Bn must be linearly dependent. So can I find a lambda such that B1 to Bn are linearly dependent? That is the question that we want to answer. Is it clear how we're moving our problem into territory that's more and more familiar? Like we started out with something, but then we didn't really know how to deal with AV equal to lambda V. So we moved it into a formulation that was more familiar in terms of null spaces. But here in null spaces again, we don't have, we don't know exactly what this matrix is. When we previously solved for null spaces, we always knew what the matrix here was. Now here, there's also an unknown in this matrix. So for this, we're going to introduce one more new piece of terminology and a new kind of quantity. We're going to introduce the idea of a determinant. And why do we want to introduce the idea of a determinant? Because we want to try and understand whether the columns of a matrix are linearly dependent or not. And we've had many, many different ways of trying to understand this. We're going to think about another way. So let's think about a very simple matrix. Let's think about this 2 by 2 matrix, A1, A2. So A1, A2 are the columns. And let's call this A, B, C, D, a 2 by 2 matrix. And we want to understand, are the columns linearly dependent? And so far, we've been doing this in an algebraic way, right? We've been saying, can we try and find linear combinations of these vectors so that they become 0? Can we find one vector as a linear combination of the other vectors? But what I want to talk about today is a geometric way to find this out. let's draw this picture. So let's say I have my space. And let's say I have vector A1 here. Right? Let's say this is A1. If A2 was linearly dependent on A1, where would A2 be? I'm seeing like these hand motions, right? So if A2 had to be linearly dependent, A2 would have to be somewhere here, right? What if A2 was somewhere like this? Is this linearly dependent? No, right? So to try and make this a little bit more mathematical and trying to understand this, I'm going to try and complete this parallelogram. Okay? So, if A1 and A2 were linearly dependent, what would the area of this parallelogram be? 0, right? You could see immediately that it's just going to collapse into a line which has no area whatsoever. But if they're not linearly dependent, what is the area of this parallelogram? How do we find that out? So if this is A, B, C, D, what is this point here? This is the first coordinate. So this is A. This is B. A2, or sorry, this will be C. Sorry about that. Our first column vector is AC, right? So AC. And A2 is going to have, this is going to be B. And this guy here is going to be D. What about this point? If I was to drop this perpendicular, what is this point? This is basically A1 plus A2, right? This vector is A1 plus A2. What do I get here? This is A plus B. And what do I get here? This I get C plus D. Does everyone see that? So I have this rectangle here of 0 to A plus B going up to C plus D, right? Everyone see this rectangle? And let's see, so we know this. So this length, this little length here is B. What is this little length here? This is C. What about this little length here? This is B. And this little length here is C, right? So with this and knowing, how many people know how to calculate the area of a rectangle? How many people know how to calculate the area of a triangle? How many people can calculate the area of this parallelogram? Take a minute and do this with your neighbors. Remember, if you have a rectangle where one side is of length A and the other side is of length B, the area of the rectangle is A times B. So how many people are done? How many people have no idea how to start? Okay. What are the other people are still working it out? Okay. 1 more minute. Okay, so does anyone want to describe how they tried to approach this? People are still working? Okay, let's give people, see a lot of people still scribbling stuff, so. Okay, I'll give you a hint. What is the area of this big rectangle, the black rectangle? A plus B times C plus D. Right? Okay, there was someone here who wanted to describe their strategy.
Yeah, it was find the area of the big rectangle, then find the area of all the other components, and factor them out.
Yeah, the idea was to say, well, let's find the area of the big rectangle and then subtract out the components of the other parts that we can easily find, right? So the big rectangle is A plus B times C plus D. What is the area of this purple shaded triangle? This is 1/2 AC, right? Is that correct? Yeah, 1/2 A times C. How many purple triangles are there? What is the area of the blue triangle? One half BD, and there's 2 of them. And then there's the yellow, but yellow won't show up, so I'm going to write it in orange. Minus 2 BC, right? So what do I get out? I get AC plus AD plus BC plus BD minus AC minus BD minus 2BC is equal to AD minus BC. So, if I gave you this 2x2 matrix and I asked you to figure out if the columns were linearly dependent or not, what number, and I told you can only calculate one number. What one number would you choose to calculate? The determinant. And in this case, what is that equal to? Determinant of, let's call this matrix A, equal to AD minus BC, right? For those of you who may have heard of determinants, who read the notes and saw that you take, the diagonal elements and subtract the product of the other diagonal elements. This is not a mystery. Do you see where this is coming from? It's simple geometry. It's saying, are these vectors linearly dependent or not? So now, if we were to think about linear dependence in 3 dimensions, what would you get? Would you get parallelograms? No, right? You would get parallelepipeds. And then you would try and look at the volume of these. In 4 space, you would start to think about hypervolumes of these things. So if you were to think about in 3-dimensional space, if you had a set of linearly dependent vectors, right? Are they going to span the 3-dimensional space? No, they will at most lie in a plane. What is the volume of a plane? volume of a plane, any planar surface is going to be 0. It has no volume, right? It has area, but it doesn't have volume. So basically, anytime you have linear dependence, you have this dimensional collapse, which means that you're going to end up with this 0 determinant. The determinant is not any mysterious thing. It's just geometry. That's saying it's one more way of trying to figure out whether your column vectors are linearly dependent or not. We've learned many, many ways of this now. Here is yet another strategy. So now that we have this, now that we have an ability to compute the determinant, can we try to actually use it to solve the problem that we wanted to solve in the beginning, right? We wanted to try and understand this notion of eigenvalues. So now we want to look at A minus lambda I times V is equal to 0. And so I want to figure out for what values of lambda can this have a can the columns of this be linearly dependent? So let's take a 2x2 example. A11, A12, A21, A22 minus lambda I is equal to A11 minus lambda, A12, A21, A22 minus lambda. And what is the determinant of this? This is equal to now, by our formula right here, A11 minus lambda times A22 minus lambda minus A21, A12. Right? And so this is equal to lambda squared minus lambda times A11 plus A22 minus, plus A11, A22 minus A21, A12. So what kind of equation is this? What is the unknown here? Lambda is the unknown. What is the degree of the unknown? 2. So it's a quadratic equation. How many people know how to solve a quadratic equation? Right? So now, for what value of lambda is this going to be equal to 0? Right? We know how to solve this. We've done this many, many times. There's in fact a formula. This is sometimes called, just for terminology, is called the characteristic polynomial. Characteristic equation. You might hear this terminology being used here and there. So just so you know. But let's try and do this now for a concrete example. So let's take the following case. Let's take, let me skip this and let's do the following setup. How much time do I have? Okay, we'll do it quickly. I'll try. Let's take A is equal to 1, 2, 4, 3. So what is the characteristic polynomial for this? I can write this out as 1 minus lambda times 3 minus lambda minus 2 times 4 equal to 0, right? Oh, sorry. Thank you. Characteristic polynomial. Yes, question? Why is the characteristic equation equal to 0? Because we want to find when can the columns of this matrix, A minus lambda I, we want the columns of this to be linearly dependent, right? What did we figure out as a condition for linear dependence of columns? We just figured it out, right? What was it? if the columns are linearly dependent, what do we know about the 4 elements? The determinant is 0, right? What is the determinant of A minus lambda I? AD minus BC. So what is A minus lambda I? 1 minus lambda, 2, 4, 3 minus lambda. What is the determinant of this? That. So why is it equal to 0? Because the determinant is equal to 0. Because we want the columns of this to be linearly dependent. Got it? So we have this. So can we write this in a form that we can easily read off the values? So this is basically, I think, lambda squared minus 4 lambda minus 5 equal to 0, right? So what are the factors of this? Everyone's seen factorization before. Lambda plus 1, lambda minus 5 equal to 0. So how many values are there for which the columns of A minus lambda I could be linearly dependent? 2, right? So if now I choose, so options, lambda 1 equal to 1 or minus 1 and lambda 2 equal to 5. And these are the eigenvalues. This gives me an eigenspace, which is the null space of A minus minus 1i. And this gives me another one, which is the null space of A minus 5i. So, can you calculate the null space of A minus minus 1i? Quickly take a minute and do this. Talk to your neighbor and calculate actually both of these. Question? I can't hear you. We want Okay, so how many people have the null space of this? What is A minus, what is A plus 1i here? How many people are done with at least the first calculation? Yeah, what is A plus 1i? Times some vector v equal to 0. So what is the space of V such that this is true? For what V's? Span of what? One, negative 1. Right? Does everyone see this? For people who don't, 2, 2, 4, 4, 0, 0, which gives me 2, 2, 0, 0, 0, 0. Right? And from here you should be able to see that this is exactly the solution. What about A plus 5i? What is this matrix? Negative 4. 4. 2, negative 2, right? And so, what V's satisfy this? What is the null space of A minus 5i? This is the span of 1, 2. Are people with me? Okay, I don't have enough time to go into a new example, which I wanted to, so I will take one question. Lecture is not over. We have 1 minute left. I will take one question. Yes, question. Lecture is not over. So the question is, what if I have a matrix times a vector and it's not a steady state vector? How do we deal with this kind of stuff? And that's exactly the example I wanted to do. We did not get to it, so we will get to it next time in class. Okay, see you Thursday.